On the farm where I'm living right now, we sometimes make campfires and let the kids stay up late to play in the dark. They run around with flashlights, through the gardens, and to the edge of the forest. But not into the forest, because at night the forest is filled with the howls of the coyotes. The howling is unnerving, even though I know that they don't pose a direct threat. Every night lately it has seemed like there have been more and more of them, and closer. I took a walk up the river one recent morning, headed towards the part of the forest where the coyotes seem to live. And I ended up here, at an empty abandoned house. Tools and building materials were strewn all over the overgrown yard, like someone had abruptly ceased a renovation project many years ago. I did not feel safe entering, even though the door was wide open. It smelled terrible for one thing, and the structure was crumbling. Although there were clear signs that some large animals were using it as a home. So foreboding, and so forbidden, both in a legal sense, since I suppose I was trespassing, but also in the sense of forbidden knowledge. What happened here? How long ago? What's up with the piano? What's up with the lamppost? Why were the tools abandoned so abruptly? From the evidence I can see today, I can reconstruct part of the story, but not all of it. On my way home, I was thinking about how we reconstruct stories to explain the past based on what we see in the present. And then I got distracted because I found another one of my favorite plants. This plant has a foreboding-sounding name. It's called a touch-me-not. But touching them is exactly what's so much fun. When mature, their seed pods are spring-loaded. They explode on touch, shooting seeds everywhere. Sometimes they shoot as far as 10 feet away. Sometimes the seed pods merely uncurl gently in your fingertips. You never know what you're going to get. The surprise is irresistible. The point is that human life is full of untellable stories, in the sense that we don't have enough knowledge to tell them. Often we're faced with evidence that only lets us reconstruct part of an explanation, or only opens up questions instead of answering them. Explanatory stories about the past may be incomplete or untellable if we're missing information. Predictive stories about the future may also be untellable when they involve random or complex events. Like, I never know in advance where the touch-me-not seeds will go if I pinch a seed pod. But a key fact we take for granted about macroscopic physical reality is that there still is a story, even if we don't know all of it. Macroscopic causality functions that way. In a way, narrative is built into macroscopic physics. I may not have witnessed what happened in that abandoned house, but I know that something happened, and then something else happened, and then something else, in a sequence of cause and effect that unfolded continuously over time, leaving marks that let me draw inferences and put together parts of the story. For example, I can tell that the house has been abandoned for many years because there's so much decay. And even with something that's random and unpredictable, like the exploding seed pods, we can do something like take a movie and reconstruct the story afterwards. Like I did here, inspecting individual frames of the movie, I can find out in retrospect how many seeds flew away in which directions. Like, here's one. And here's a couple more. The point I want to emphasize in this video is that causality does not seem to work the same way on the quantum scale. Quanta behave in ways that resist narrative, and while we're still able to make predictions about their behavior, and we're still able to use evidence to infer explanations, we run up against some apparent limitations that seem to go beyond the everyday problem of just not having all the information. So don't panic at the density of information in this image, nor get too distracted with all the silly-sounding names that you see. I have this here because I want to remind you of the kinds of things I mean when I say quanta. This chart is something like a periodic table for the fundamental or elementary particles, the elementary quanta. That is, the basic building blocks of the universe as far as they're currently known to physics. Each entry in the table is a different type of particle, or quantum. So when I talk about the quantum realm, or how causality functions for quanta, I'm talking about the behavior of these kinds of things. Or possibly these kinds of things, because it turns out that collections of small numbers of fundamental quanta, like you have in atoms or even some molecules, can in some conditions act just like individual quanta. But I'm not talking about these kinds of things, because by the time you conglomerate enough quanta together to make things like biological structures, cells and plant pieces and things like that, or any macroscopic objects, apparently the rules change, for reasons we don't completely understand. So okay, the most important quanta in this image for understanding everyday reality are these four. We encountered up quarks and down quarks and electrons in the previous video when we talked about the constituents of atoms. The fourth one that I've highlighted is the photon, which is the quantum scale basic component that makes up light. The symbol it's given looks a little bit like a Y, but it's really the Greek letter gamma. So two of the most common quanta we discuss in quantum physics are the electron and the photon. Now, in the first video of this series, I made a big deal about distinguishing between matter and light on the basis of the fact that matter has the property of mass and light does not. This is true at the quantum scale too. The electron is an example of a fundamental particle that has mass, and the photon is an example of a fundamental particle that does not. This affects, among other things, the speed at which they tend to travel through space. But in this video, I'm not going to talk about the ways that these particles are different, but instead highlight some behaviors that they have that are in common, and that, in fact, all quanta have in common. And before I talk about those behaviors, I want you to imagine how we might go about doing an experiment to learn something about how an individual electron or an individual photon behaves. They're far too tiny to see in any straightforward way. I can't just take a movie of them like I do when I'm experimenting with plants or something like that. Also, where would we get them? What kinds of tools would we need to track what they do? So I'm showing a picture of a notebook here because I want to suggest the idea that experiments in physics are attempts to tell stories. And without implying that we should personify electrons and photons, which we shouldn't, they are the central characters in typical quantum physics experiments. And to get them, we'll need some kind of a device that I'll call a source that produces individual quanta in a controlled way. You might think of this as a little photon gun or an electron gun, if you don't mind the violent metaphor. And the experiment will involve sending those characters, the individual quanta, into an apparatus or environment that will force them to do something, to interact with something. Finally, we use some kind of sensor or detector to see where they ended up, or to measure how their properties have changed. And then we use the information to reconstruct the story, to figure out what plot unfolded as the quanta invisibly traversed the scene. I've illustrated these ideas with empty generic boxes here, in part because the actual tools and devices that are used in physics experiments are pretty unfamiliar to most people. And the kinds of tools that we would use would be different if we were experimenting with photons versus experimenting with electrons. Actually, with photons, the tools that physicists use aren't that different from things that we use every day. For example, how do you make a bunch of photons? A flashlight will do the trick, or a laser. In a way, any kind of object that's in the environment counts as an apparatus, like this hand. And the pixels of a digital camera work to detect the reflected photons one by one. And with a photograph, we can reconstruct a story. We can reconstruct the story that the photons left the flashlight, struck the hand, and then ended up in the camera. It may not be quite as straightforward to do experiments with electrons, but collecting a bunch of electrons for an experiment also isn't that hard. Electrons are everywhere. Simply rubbing a balloon in a child's hair is enough to collect a bunch of extra electrons on the surface of the balloon, which explains the effects of static electricity. Some simple electron sources that physicists use in labs are based around the same effect, just using friction to generate static electricity, and then controlling where the electrons are able to go. And I don't know if you've had this experience, but you may have noticed that sometimes static electricity, that is, the movement of electrons, can result in little visible flashes. We have a couple of blankets here that are particularly fun to snuggle with at night because they tend to flash with tiny static discharges that you can only see if it's very dark. So the point to all of this is to motivate that a basic setup for an experiment with quanta might be represented with this sketch. On the left is the source. Maybe it's a laser, maybe it's an electron source that's based on static electricity. And on the right is some kind of sensor. Maybe it's a camera, or maybe it's a screen that creates a little flash of light every time it's struck by one of the quanta. And in the middle is where we might put various barriers or other things for the quanta to interact with, using the changes in the pattern in the detector to reconstruct the story of what the quanta do. And without anything in the way, we might expect to see something like this. This is why we call quanta particles sometimes. When we detect them, they tend to be detected in one place at one time, like a particle, like a dot. But certain barriers that we put in the way reveal different behavior. Like, for example, stick a barrier in the way that has two slits in it. Obviously, that's what you would choose, right? I mean, the double slit experiment. I mean, it's kind of a cultural icon in and of itself. And obviously, that's what I'm building up to. So I want to talk about what the double slit experiment is and what I take from the double slit experiment. But to be honest, I am going to assume that you've already heard about it, and I don't really want to explain it all from scratch. I just want to comment on some of the things that are often misunderstood. So if you don't totally know what I'm talking about, then this is a good point for a little intermission. Intermission, there should be music. I am singing a little song about quanta. It is so embarrassing, except that I am such a dork that honestly nothing embarrasses me. Okay, did you note the timestamp on the video? Hopefully you ducked out and ducked back in as needed, and we're going to pick up with the punchline, which is that the double slit experiment, when we actually perform this kind of experiment, gives us a pattern of dots in our detector that looks something like this. And since you now know about the double slit experiment from whatever else you looked up on the web, you know this pattern is really weird, and it's evidence for something that physicists call the wave-particle duality of quanta. But also, if you're paying attention, probably you have a lot of questions. Like, first of all, why am I not showing a photograph of a real experiment here? If this is so important in the history of physics, which it is, why is there not some snapshot of some old white guys with beards, because that's how science works, who actually did this experiment the first time around and made some amazing discovery with it? Well, to address that, there have been literally gazillions and gazillions and gazillions of iterations of the double slit experiment. In fact, you can look up a way to do this at home with lasers if you want to. And that's partly why nobody ever shows just a single photograph of some particular historical discovery. Those experiments through history have explored light, electrons, atoms, molecules, and even some macroscopic phenomena like water waves. And for exactly that reason, because there's not one double slit experiment but many, it's easier to represent the idea generically. Also, the real tools that physicists use in their experiments are sometimes flashy looking and cool, but they aren't exactly easy to understand if you're not an expert. So we'll stick with the cartoon version. But then, the next obvious question is, why exactly is a barrier with two slits such an interesting thing to study? The reason for using a double slit specifically is that it's an apparatus that provides more than one path through space to get from the source to the detector. And the reason that that's an interesting thing to do is because wave-like phenomena will behave in a different way from particle-like phenomena when there's multiple paths available. So a double slit apparatus has historically been useful for studying whether things behave more like waves or like particles. But then wait, aren't all the quanta we might put through a double slit experiment technically particles, or at least made up of particles? I mean, the chart was labeled that way. But physicists have discovered that the things that we call particles don't always behave like particles. Sometimes they behave like waves. So here's a picture of some ripples in a river to illustrate what I mean. And in the picture, there's also some little bugs. The bugs are kind of particle-like. Each bug just exists at one place at one time, and that's what we mean by particle-like behavior, existing at one place at one time. Meanwhile, look at the waves. Can you identify anything in here that you would call one wave? Intrinsically, the idea of one wave is kind of a little bit ambiguous. And even supposing that we take one ripple as defining one wave, that ripple is simultaneously in multiple places at once, and it's simultaneously taking different paths through the water at once. And if you get a whole pattern of ripples combined with another pattern of ripples, they can overlap or combine in complex ways that cancel out in some places or add together in others. Waves are still something that can be described in narrative terms. I mean, we can make movies of them. Everything proceeds through a straightforward logic of cause and effect. But the narratives associated with waves are different from the narratives associated with particles, because waves can do things like take multiple paths at the same time. They can also combine and cancel each other out, so that single waves can exist in some places and not exist in other places at the same time. Honestly, it's just not that weird for waves. When you send waves through a barrier that has two openings, what you end up getting is an interference pattern between the part of the wave that went through one slit and part of the wave that went through the other. So one thing that's deeply weird and messed up about what we see with quanta in the double slit experiment is that their behavior seems to be a hybrid of the wave and particle ideas. Physicists use the term wave-particle duality for this. On the one hand, when detected, each quantum is in one place at one time, like a particle, like a bug, like a seed. But when we look at a bunch of them, it becomes clear that some aspect of their behavior is wave-like too, because the pattern that emerges shows that each quantum is somehow influenced by multiple paths through the apparatus, not just one path. And that's a lot more like a wave. And this is one way that the double slit experiment shows how quanta aren't really able to be described in narrative terms. For an electron or photon to simultaneously be a wave and a particle is a self-contradictory merging of stories that leaves us with nonsense. Try to tell the story of how this pattern emerges, and you'll end up saying weird things like, the quantum has to go through both slits and then somehow recombine with itself at the detector. Or, the quantum has to be a wave up to the point of detection when it collapses to a particle. Those are attempts to tell the story behind the pattern that we see here, but the experiment doesn't show any of that. It just shows what it shows. And what it shows is that quanta merge self-contradictory behaviors. There is no ordinary story that we can tell. And then, we add the observer effect to all this. The observer effect is the name for the fact that what quanta do seems to depend on context. The term observer effect causes a lot of confusion. A conscious observer is not necessary for the observer effect to occur, and a concrete way it might be demonstrated in the double slit experiment is by putting a second detector system right by the slits to see which path the quanta take. And if we do that, what we end up with is a different pattern, much more particle-like, for both detectors. And maybe in a way that makes sense, because to put a detector in the way we had to force the quanta to interact with something, and evidently those interactions change what happens. What we find in current day experiments is that the behavior of the quanta, whether they show this wave-like interference pattern, or this more particle-like pattern, depends not on whether there's a conscious observer, but on whether any information is generated about which slit the quantum goes through, even if that information is determined indirectly, like by a process of elimination. And honestly, that really is deeply spooky. If the story would be totally changed by capturing information about that story, can we really imagine that there was a story at all? That's what makes this experiment profoundly strange. Not only does the pattern simultaneously reflect two contradictory behaviors, but if we try to tease out how that self-contradiction comes about, it stops happening. Which means that quantum stories are untellable in a very different way than macroscopic stories. They don't appear to be something that we can describe through narrative at all. But, maybe that's not so weird. We're used to stories that involve contradiction, blending truth and fiction, and we know that the ability to capture a movie of something doesn't mean that we capture all of it. But still, even though I know that not all stories are simple, there's something about this that I find spooky as hell. Way creepier than the Howling Coyotes and way creepier than any ghost stories I've ever heard.